Hey everybody, this is going to be a video outlining the concept of molarity. So molarity is a measurement of concentration. Concentration essentially just communicates how much solute is in the solution, or a more simple way is just how much stuff is in there. So when you're talking about a solution, you've dissolved a solute into a solvent, you now have the solution, and you might want to know how much stuff is in there. Okay, so how much solute is in there now that it's actually in there? Like if you just find a solution, how do you know how much stuff they put in there? Okay, molarity is a way to do that. There's actually a ton of ways to measure concentration. Percent by mass, percent by volume. This is probably what you're the most familiar with. If you've ever looked at something that says like 100% fruit juice, or the active ingredient is 5% acetaminophen or something like that, those are all measuring concentration. So whether that be by mass or by volume depends on the product. So if it's a solid, if it's a liquid, if it's a solution, etc. You might have seen something like parts per million or parts per hundred, parts per billion. That's talking about like really, really small concentrations. So if something's like 2 parts per million, that means if you took 1,000,000 parts of the solution, 2 of them would be the object of interest. In this class and in chemistry, the one that we by far use the most often is molarity. And as you could probably assume, it's because we use moles in chemistry. Because atoms are so small, 1 mole, 6.02 times 10 to the 23rd, is actually a reasonable amount. So, what is molarity? It is a communication of how many moles there are within the liters of solution. So we've got a nice equation for that. Moles per liter is equivalent to molarity. So this capital letter M is our variable for molarity. Sometimes it's just written as moles per liter. I tend to use the M the most often because I'm lazy and that's easier. But please note it's just a capital letter M. So essentially the higher the molarity, the higher the concentration. So if something is like 10 molar, for example, so 10 molar would be 10 moles per liter, there's 10 moles in that 1 liter. So that's could be fairly high, fairly concentrated depending on what you're talking about. A low concentration would be a low molarity, so like 0.01 molar. So there's 0.01 moles in that 1 liter of that solution. So the numbers can be relative depending on what you're talking about, but when you're getting that number, so like 2 molar, there's 2 moles per 1 liter of that solution. So one of the things I need you to feel comfortable doing is essentially just solving problems with that equation. So we've got moles per liter is equal to molarity. So our first question here is if you have 0.047 moles of sodium nitrate in 1,250 milliliters, what would be the molarity of the solution? Well, you would take your 0.047 moles, and here's the first thing I want to point out. Notice that molarity is always measured per liter. So if you've got milliliters, you're going to need to modify that. So if I've got 1,250 milliliters, I can divide that by 1,000 in order to get to liters. So this would be 1.25 liters. So 0.047 moles divided by 1.25 liters. And when we math that, boom, boom, boom. And how many sig figs? Think about it first. 2. Leading zeros don't count, so 0.047 has 2. I'm getting an answer of 0.038. And I'm going to use capital letter M, molar. I'm going to write that nicer. Boom. Moles per liter is also an acceptable unit, whatever you prefer. So another one. If you want to make a 0.15 molar solution and you have 0.26 moles, how many liters of water would you need? So I also need you to be comfortable rearranging this equation. So this one, you have the desired concentration you're looking for. You have the amount of solute you have in front of you. You just want to know how much water you should grab. So if I rearrange this and multiply by liters on either side to get liters out of the denominator, didn't want to do that one. Boom. I've got moles is equal to molarity times liters. I'm solving for liters though. Divide by molarity on either side. Boom. Moles per molarity is equal to liters. So that's going to be my equation here. So 0.26 moles over 0.15 molar. I'm going to need 2 sig figs again for this. And so just 2 sig figs, I'm getting 1.7 liters. That'd be my final answer for that. So simply taking the equation, rearranging it, depending on the situation in front of you is one thing you need to be able to do. So you might have been thinking to yourself, When would I find myself in those previous situations? You probably weren't. But here's one that you're probably more likely to find yourself in. If you want to make 50 mils of a 1 molar solution of copper 2 nitrate, how many grams would you need? So most of these solutions we're going to be making are going to be ionic compounds and water. Ionic compounds are all solids at room temperature. And so if you're going to require a solid, the easiest way is going to be measuring the mass of that solid. You can't just look at something and know how many moles it is. That's why we've got this concept of molar mass and all the stoichiometry that we've already done up until this point. So here would be how you would actually prep a solution. So anytime in class you've used a solution, so an aqueous solution in any chemical reaction lab or anything we've done, I made it ahead of time, and this is how I would have done it. So if I needed 50 mils of a solution for a particular lab and I wanted it to be 1 molar, because that's a reasonable concentration, here is the work I would have done in order to do it. First, I would have done the math. So if I've got 50 milliliters and I've got molarity, and my equation is moles per liter is equal to molarity. If I've got milliliters and molarity, I could convert the milliliters to liters, and then I can solve for moles. So that's what I would do first. So by rearranging this, I get moles is equal to molarity times liters. So I'm going to take my molarity, which is 1.0. I'm going to multiply that by the liters. Remember, you can't use milliliters. This has to be in liters. So I'm going to divide this by 1,000. And I'm going to get 0.0500. Note that I took all those zeros with me because this had 3 sig figs, so I wanted to make sure it still had 3 sig figs down here. Anything times 1 is itself. Note this only has 2 sig figs though, so my final answer will be 0.050 moles. So that's how many moles of copper 2 nitrate I'm going to need in order to dissolve this and make my solution. Well, I can't measure in moles, so what I can do then is I can take my amount of moles and I can convert my moles to grams using the molar mass. My compound here is copper 2 nitrate, so lots of good review in here. So copper is Cu, nitrate is the polyatomic ion NO3. The Roman numeral 2 here is representing the fact that copper has a +2 charge. It's one of those transition metals that can have variable charges. Nitrate has a -1 charge. So if this is a +2 and a -1, I'm going to need 2 nitrates. Remember, if you've got multiple of a polyatomic ion, you need parentheses around it. Whew. So let's go ahead and figure out the molar mass of this. So I need the molar mass of copper, which is 63.55. Nitrogen is 14.0. Oxygen is 16. That's everybody, yes. So 63.55, 14.01, there's 2 nitrogens. And oxygen, there's 6 of them with the 2 and the 3. So add all these puppies together. 187.57 is my molar mass. And I'm going to multiply that by the amount of moles that I need. And to 2 sig figs, I'm getting a final answer of 9.4 grams. For my final answer. All right. So that's all the math I would have done. Real life, true story. I do this all the time. So that's the number I'd get. I'd be like, okay, cool. I need 9.4 grams of copper 2 nitrate. So then I would grab my copper 2 nitrate, which is blue, right, because of the copper +2 ions. I would dish it onto the weigh boat until it says 9.4. And here's the new part. I would then pour it into a volumetric flask. These are very fancy flasks that are designed to only measure one amount. This one in particular only measures 50 mils, because if you noticed, my question wanted me to solve for 50 mils. So that piece of glassware can only measure 50, not 10, not 30, only 50. But it measures 50 more precisely than any other piece of glassware we have. So that's why we use it. So I'm going to dump the 9.4 grams into it, and then I'm going to dump some water into it. I'm going to dissolve as much of that as I can. And then, it's hard to see in the video, obviously, but there's a really thin gray line, maybe you can kind of see it, that's on the volumetric flask, and you fill the water up until that line. You make sure everything's dissolved, and then boom, you have your 1 molar, oh, that bottle says copper sulfate. We did copper nitrate. and then you would have your 50 mils of your 1 molar solution. So this is a much more practical way to make a solution, figuring out the amount of grams via the math, dissolving it into the water in a volumetric flask, and then going from there. So another way in order to make a solution, keeping in mind its molarity, is to perform a dilution. So dilutions are when you have a higher concentrated solution in front of you, and you're going to take some of it out and dilute it. Diluting it is essentially going from a higher to a lower concentration. So for example, maybe you took a sip of lemonade that you made from home and you're like, that's way too sour or that's way too sugary, one of the two. You would maybe dilute it. So you take that high concentrated, really sour, sugary mixture, and then you would add water to it. By adding water, you are therefore lowering the concentration. So that's the idea of a dilution. In chemistry, though, we generally have a very specific targeted amount that we're looking for. So for example, maybe we have a stock solution of 0.5 molar sodium hydroxide. Okay, so that's already existing on the shelf. And I want to dilute it to 0.12 molar. So it's 0.5 currently, I need it down to 0.12. And then I need 550 mils of this now 0.12 molar I'm looking for. How would you make it? I'm going to go ahead and just zip on down here. And we actually have an equation for this, the dilution equation. M1V1 equals M2V2. So basically the idea is this, molarity times volume. So if I go back to my molarity equation super quick. Okay, if I rearrange this really fast, liters times molarity is equal to moles. One of the liters is a measurement of volume. So if I rewrite this, see what's happening? Molarity times volume equals molarity times volume. Essentially, molarity times volume is equal to moles. So if these two solutions have the same number of moles, you can fluctuate the molarity and the volume accordingly to get them to still equal one another. So basically what you do is you take the higher concentrated and you figure out how many moles of the solution you would like to take out. Then you put that back in that volumetric flask, so the same flask we were talking about before, and then you add water to it to dilute it. So if you look at these two pictures, notice we've got the same amount of moles. All we've done is we've added water in order to further dilute it. So if you know how many moles you want, you can figure out how many moles you need to get from the previous solution, and then by adding water, you still have the same amount of moles. So coming back up to this initial problem here, this 0.51 molar, that's my M1. So that's how the molarity of the solution that currently exists. 0.12 is M2, that's the molarity of the solution I'm trying to get. And I'm trying to get 550 milliliters of that solution, so that's automatically V2. So what you're solving for here is you're solving for V1. You're essentially trying to figure out how much of that higher concentrated solution you are going to dilute. So if I plug everything in here, equals 0.12 molar, 550 milliliters. Notice for this one you can keep it in milliliters, because essentially if both of your volumes are in milliliters, everything kind of cancels out accordingly. So dividing by 0.50 on either side, help if I wrote it right. There we go. So 0.12 times 550 divided by 0.5, I'm getting an answer of 132 milliliters would be my V1. So essentially what I figured out here is, you know that 0.5 molar, that initial concentration that I had to begin with? What I would need to do is I would need to take 132 milliliters of that, so 132 mils of the 0.5 molar, the higher concentration. And if I take that and if I add water to it until I get to my 550 mils, my desired concentration, I now would have a 0.12 molar concentration. And that is because M1 times V1 is equal to moles. So I've got equal moles in both solutions. Here's another example problem worked out really quick if you need another example of a dilution problem. Another thing we can do, because molarity lets us solve for moles, we can do all of that stoichiometry that we used to do. Yay! So for example, if you react 35 mils of a 0.5 molar solution of lead-2 nitrate with excess potassium chromate, how many grams of the precipitate would form? I want to see if you can figure this one out on your own. Here's my hint. Given these two numbers, can you solve for moles? If the answer is yes, you should be able to do everything else via stoichiometry. All right, here you go. So this one also had some review with writing out a double replacement reaction, doing a little bit of stoichiometry, but essentially once you've got moles, everything else plays out how it used to.